everyone. Today we're going to talk about the more advanced things that are fundamental to how derivatives work. And I'm going to start off with writing dx open bracket of 3x plus 4y equals dx of 12. So as we know already, using either the power rule or if we did a limit definition for some reason, the derivative of 12 is 0, as is with any constant. And then here is a little bit complicated because we have to take the derivative of y. Excuse me? Exactly. So this is something that we can split up into like dx of 3x, so 3 plus dx of 4y. And then it's a little confusing on what to do, but essentially we're going to take this 4 out. That's another nice thing. Plus 4 times dx, just y. And you might ask, well, how do we do this? This involves something called implicit differentiation, I think. Yes. And I will talk about differentiability later because it is something that I should have talked about way earlier, but I kind of glossed over it because it deals more with limits. But you also have to know derivatives for it. But the way to do implicit differentiation is that we pretend that this y is an x, just for a little bit. And it's like, okay, well, if this was an x, the derivative of this would be 1. But we also pretend that it's kind of like a chain rule. Well, it's 1 here, but it's not truly a 1. We have to multiply it by the derivative of y, which still doesn't make sense because we just write it out as dy dx. This kind of blew my mind when I first found out about that. So we have this, and now what we have to do to find the derivative is to solve for dy dx. So obviously we're just going to put dy dx. I'm just doing some algebra stuff in my head because I don't feel like writing all of that out. Negative 3 over 4. That's the derivative for this function. Now that we know implicit differentiation, or the part that I actually want to explain, that implicit differentiation is more of a intermediate technique. I just did not cover it because it glossed over my head because I haven't done one of those in a while. But now, let's say I have an evil ass function. So we're going to have 3x plus 4 times 4 minus 7x. I'm going to say this is the third power, this is the second power. It would be funny if I just did this, actually. Now, if I want to take the derivative of this, well, first I'm going to take out this 41 plus 3 to the power of 5. And taking the derivative of this, we're not going to use a product rule with 2 chain rules in it and a quotient rule. That's ridiculous. It's just ridiculous. So what we're going to do is that we're going to say that this is equal to y, and we're going to take the natural log of both sides. So this is its own ln, and then if I rewrite this other side, is ln of y. So rules that I'm assuming you already know because calculus doesn't reteach logarithm rules. All of this multiplication and division just becomes subtraction and addition inside the inverted world of logarithms. So what this actually is ln of 44. Alright, and the exponents become multiplication. 5 times ln of 44 plus 3 times ln of 3x plus 4 plus 2 times ln of 4 minus 7x minus ln of x plus 1. This is not that horrible. It's still like big, I guess. I'm gonna zoom out like this so I can actually. Like, this is still like a pretty big thing to take, but it's not horrible anymore because you don't have to do 20 different techniques all intertwined with each other. So, and all of these are just their own tiny little chain rules as well. So this is 5 times, well, this is a constant, so this is 0. 0. So we can move on to this thing. I'm just gonna, my signature, nice dark red color, I like, cross that out. This is 3 times 3 over 3x plus 4 using the chain rule plus negative 14, or I should do it as 2 times negative 7 over 4 minus 7x. That's the other one. Minus is just 1 over x plus 1, thankfully. Equals, well, ln of y, if we use implicit differentiation, which I just explained, 1 over y times dy dx. And this is why you shouldn't really use this for anything that is in FRQ, because to get the derivative of this, we still have to multiply this y back into the function. So what our actual answer is dy dx equals y times all of this stuff, which I already put. So 9 over 3x plus 4, extend that out, minus 14 over 4 minus 7x minus 1 over x plus 1. That's that derivative. I'm going to make this bigger now. There we go. Zooming back in just a little bit. Thing that I did not mention last time, but I should still talk about because I did forget it, is the derivatives for arcsine of x. I'm just gonna write that out. Arcsine's derivative is 1 over the square root of 1 minus x squared, I think. Yes. The derivative for secant, right? Arcsecant, it should be secant arcsecant of x is equal to one that's actually the most complicated, but it makes it the most recognizable. There's an absolute value of x because of the way that secant and cosecant are as functions with the whole thing. So square root of that time, or absolute value of x times the square root of x squared minus 1. And then I would say that arctan is the simplest, where it's tangent x is equal to 1 over x squared plus 1. And you might ask, okay, well, this is sine, secant, and tangent. What about cosine, cosecant, cotangent? Well, those are actually pretty simple, because if I were to just write this d of cosine of x equals -1 over x squared minus 1. We take this. Well, actually, you know what? I'm going to write this in a more efficient way. This is equal to negative d dx of sine inverse sine. This is just cosecant -1, whoops, equals negative d dx of secant, arcsecant. You might notice the pattern, which honestly makes it where, hey, instead of having to memorize 6 things, you only have to memorize 3, which is really nice. Equals negative tan minus 1 x. Boom. Those are that. That's those are these things. That's just the small thing I forgot to mention. But those are something you can really only memorize. I don't even think I got explained in class how those like conclusions were made. It's just something where it was like, hey, this is that. Please memorize it. And I think that's it. I'm so used to the physics video I recorded yesterday that ended up being 40 minutes. That this calculus video did not take that long, but I guess I also don't do problems much when talking about math, which is funny because for math, studying for math, I would say do more problems